Hello everyone, welcome back to the channel. I am Nikhil Kumar. Till now in this particular series we explored container pieces by species, namespaces for isolation, Cgroups for resource control, root file system separation and networking using veth and bridges. But today we stop learning concepts separately and finally combine everything together. So in this video we are going to build a container runtime from scratch. No Docker, no Containerd and no Kubernetes, just Linux kernel primitives. And by the end we will launch our fully isolated container with file system isolation, namespaces, process isolation and resource limits. Before touching commands, let's understand what a container runtime really does. From outside we just type a docker run and it feels like Docker creates a container instantly. First, Docker talks to Containerd, which is responsible for managing container lifecycle. Then Containerd calls runc, which is the most important part here, because this is where the actual container creation happens. Runc uses Linux primitives like namespaces for isolation, Cgroups for resource limits, rootfs for file system separation, and networking setup for connectivity. So what we are going to build today manually, Docker is doing the same thing automatically through runc. That's why I say Docker is not magic, it's a very good automation layer on the top of Linux. So the real container is created by Linux, Docker is just making it easier for us. Let's start with file system isolation because every container needs its own file system view. So for that I have already created a helper script to generate a minimal root file system. So if I do ls here, so this is the script that is build rootfs.sh. So this particular script creates a rootfs file system for us. So for that we need to run command that is build rootfs. And along with that, we need to specify the binaries which we need to place it under the rootfs file system. So first of all, we need to provide the bash, yum, ip, rm, mount, umount, ls, ping, mkdir, pivot, root. So these are the binary which I am going to place it under my custom rootfs file system. So let's press enter here. So as you can see, it created a rootfs file system under the same directory. If I do ls here, so we can see the rootfs has been created, and to test that we can use the chroot command. So we can use the same command and if it enter, so we are inside our custom rootfs file system. So if I run ls here, so I am not able to run it because in this particular file system we have placed all the binaries under the /bin folder. So for that we need to set the path for the same. So we can use export path equal to /bin. So if I run the same command again, so it's working fine, and as you can see it's showing the rootfs file system only. It's not showing any of the files coming from the host system. And if I'm going to run ip-addr command, so this is also working fine because I have placed this particular binary under the bin folder. So these are the binary which are placed under the rootfs file system. But if I'm going to run curl command, so this command will fail because this particular binary is not being placed under the rootfs file system. So we are going to use this particular rootfs file system inside our container. So let me come out of it. So now let's create an actual container process using the namespaces. So for that we can use a unshare command. So unshare -net -mount -uts -ipc fork mount -proc and the PID. And at last bash, so it will give us a bash shell to us. So if I hit enter, so now we are inside a container like environment. And if you want to understand each option of this particular command, and I have a dedicated video on each of the topic, I would suggest you to go to the series from the starting, so you will get a proper understanding about the network namespaces, mount namespaces and the Cgroups. So at this point we are inside a container like environment. So to verify that we can use a echo $$ command. So this particular command prints the process ID of the current shell. If I hit enter, so that is process ID 1. That means it's a first process of the container. And if we want to see the processes running inside this particular container, so we can use ps-ef command. And we can see only one process is running, and that is bash, and the process ID of that is 1, which is the same output which we got from the echo $. Now here's something really interesting. If we open another terminal, can we still attach to this running container? So to check that, let's duplicate the session and let's enter the password. And if I run the ps-ef command, so right now we are at the host system. But if we want to connect with this particular container, so first of all we need to get the process ID of that particular container. So we can use a ps command. So ps-ef and grep for unshare, because we have used the unshare command to create a container. So this is the process ID of the container, that is 5867. So now let's connect with that particular container. So for that we can use a nsenter command. along with -- target, and the target is 5867, and we need to specify the different namespaces which we want to use. So we are going to use the same namespaces. So let's go back, and here we can use this particular namespaces, and let's hit enter. So as you can see, we got an error because nsenter doesn't use the fork. So let me remove this, and let's remove the mount-proc as well. And at last we need to give a bash so that it can give a bash shell to us. So let's hit enter. So now we are inside our container. This is exactly how debugging tools entering inside the containers. So right now if I run the hostname command, so this is the hostname which is coming from the host machine. If I come back to the container and if I run the hostname command again, so this is the same hostname because we haven't changed the hostname. So now let's change the hostname here. So hostname container -1. So now we have changed the hostname here. So to verify that, let's go back to the terminal and run the same command again. So now we can see the container -1 has been updated because we have attached to the container that is the same one, that is a 5861 which we have just created using the unshare command. So now we are inside the container namespaces, but the file system is still using the host file system. So let's get back to the previous terminal, and if I run ls here, so we are still able to see the file system from the host view. So now let's replace the container's root file system. So for that we are going to use the rootfs which we just built using the helper script. So if I run ls rootfs, so here this is the rootfs file system which we have built. So now to replace the root file system, we are going to use a pivot root command. But pivot root needs a place to temporarily store the old root. So for that we have already created a directory called old_root. So this is the directory which we are going to use to place all the old root temporary file system. And one more important thing, pivot root will only works with the mounted file system. So what we are going to do, we are going to use a mount command to mount this particular file system. So for that we are going to use mount --bind rootfs and rootfs. So bind mount is required before the pivot root can work properly. So let's hit enter here. So now we have mounted this particular file system, and let's go inside the rootfs. So now we are inside our custom rootfs file system. So now let's replace the old file system to the new custom rootfs file system. So for that we can use pivot_root dot old_root. So pivot_root will replace the current rootfs file system. Dot means the new root, and old_root is the old file system location where we are going to place all the file system. So let's hit enter. So now we have replaced the containers file system with the custom rootfs file system. So if I run cd space enter, so as you can see we are not having any /root directory in this. And if I run ls here, so ls will also not work because it's looking for the binary under the /usr/bin. But in this custom rootfs file system, we have placed all the binaries under the bin folder. So for that, we are going to set the path first. So export path equal to /bin. So now if I run cd/, so now we are at the /drive, and if I run ls here, so we are able to see the rootfs file system only. And if I run ls old root, so we can see all the host file has been moved inside the old_root directory. So using the pivot root, we have replaced the current file system with the custom rootfs file system. But normally container runtimes unmount the old root completely. But for learning purpose, I will keep it mounted so we can inspect things safely. Now container has isolated file system and processes. Next, let's control the resources. So for that, we are going to apply the resource limit using the Cgroups. So first of all, let's create a Cgroup. So for that, we can use mkdir /sys/fs cgroup and /demo. So as you can see, this particular command got failed because after pivot root we changed the process root file system. But notice something important. Our new rootfs file system only contains the directories like /bin, lib, sys and the proc. But these are just empty directories. The actual kernel virtual file system are not mounted automatically. So when I tried to access this /sys/fs cgroups, it failed because sysfs itself were never mounted inside this new rootfs file system. So container runtimes like Docker or Containerd automatically do this setup for containers. But since we are building the container manually, we must mount the kernel virtual file system ourselves. So for that we are going to use a mount command. So mount -t sysfs and /sys, because this is the directory which we have created, but at the time of creation it has been created as an empty directory. Let's hit enter. So now we have mounted the sysfs to the /sys directory. So if I run ls /sysfs and cgroup, So now the kernel interfaces becomes visible inside our isolated file system. And this is why a container is much more than just a root file system. So now let's create a C group again. So we are going to use the same command, that is mkdir, and I'm going to create a C group with a demo-container. So as we can see, it again failed. So when we use a pivot root, we move into a brand new file system namespace. But the kernel mounts from the original host were not automatically available here. So /sys existed, but it was actually empty. So if I run /sys, we can see the files. This become available after mounting the sysfs. But still inside these particular directories or interfaces, we have nothing. So if I run fs, we have C groups, but inside the C group, we have nothing inside it. So that means we are still not done. Even after mounting sysfs, C group was still empty because C groups are actually another separate virtual file system. This is a C group v2. So for that, we are going to create a mount point for that. So mkdir -p and sysfs C group. And now we are going to mount the C group v2. So for that, we can use mount -t C group v2 none and to this particular directory. So let's hit enter. Oh, so there is a typo. So I need to use C group 2, not v2. So now it worked fine. So this mount exposes the Linux resource control interfaces. And this is how container limits CPU, memory, processes, and even IO. So if I run the same command, that is ls to the C group. So now we can see all the files directly managed by the Linux kernel. So container runtimes like Docker automatically configure all of this for us. So here we are doing it manually. So we need to perform this step before applying the C group. So now let's apply the C group. So for that, we are going to use the same command, that is mkdir /sys and this one. And here I'm going to create a C group with the name called demo-container. So let's hit enter here. So now we are able to create a new C group with a name called demo-container. But let's apply the memory limit. So first of all, let me clear out the screen. Let's run echo 200M and I'm going to place it under the /sysfs C group demo-container and /memory dot max. So this particular command limits a container memory to 200 MB only. So let's hit enter here. So now we have set the memory limit to 200 MB, but we need to apply it to the container. So for that, we can use echo $$ and this particular path and the C groups .procs. So here we are adding the current shell inside the demo container C group under the cgroup.proc file. So let's hit enter here. So now we have applied the resource limit to this particular container using the C groups. So now our container has isolation and resource limits, but still no network. So now let's give our container real network connectivity. So before that, let's run the IP-addr command. So here we can see only loopback is there and that is also down. So now let's give this container a real network connectivity. So for that, we need to create a virtual cable. So inside the host, we are going to create a virtual cable with two endpoints. One end will be connected to the container and another end will be connected to the host. So for that, let's get back to the host and let me come out of this container. And now I'm inside the host, and if I run the host name, we can see the host name, that is master1. So let me clear out the screen. So now let's create a virtual cable with two endpoints. So for that, we can use IP link add veth-host type veth peer name veth-container. So this particular command will create a virtual cable with two ends. One end is veth-host and another end is veth-container. If you want to understand network connectivity in much detail, I have a dedicated video on the container networking. I will add a link in the description. You can check it out so you get a better understanding what's happening behind the scene when we run this particular command. So let's hit enter. So now we have created a virtual cable with two ends. If I run IP-addr, so we got a two interfaces. It's just like a virtual cable with two ends. So now what we're going to do, we are going to move this particular interface to the container side. But for that, we need to get the process ID of the container. So we can use ps-ef and grep for unshare. So this is the process ID of the container. So we are going to move this particular interface inside this particular container. So we can use IP link set veth-cont netns and to the process ID, that is 5867. So what we are going to do? So we are going to move this particular interface, that is veth-container, to the network namespace of 5867 process, that is a container. So let's hit enter. So now we have moved the veth-container interface to the container. If I run ipaddr, so we can see the veth-container has been moved from the host. And if we come back to the container, and if I run the same command, so we can see veth-container has been moved inside the container. So now it's time to configure the networking inside the container. So first of all, we need to assign the IP address to this. So we can use ipaddr add 10.0.0.2/24 and dev, that is device, that is veth-container. So now we have assigned the IP address. If I run ipaddr, so we can see the IP address has been assigned. So now let's bring these two interfaces up. So IP link set veth-cont up. So similarly, we are going to bring the loop back up. So if I run ipaddr, so now we can see the container side networking has been set up properly. But we need to configure the another end of the cable, which is at the host side, that is veth-host. So for that, we are going to assign the IP address, that is ipaddr add 10.0.0.1/24 and dev, that is device veth-host. And we need to bring this up. So IP link set veth-host up. So if I run ipaddr, we can see the veth-host has been configured properly and it also up. Now let's try to connect with the container. So we can use ping command and the container IP address, that is 2. So now we can see the container and host has a connectivity with each other. And if I try to connect with the host from the container, so ping -c3 10.0.0.1. So we can see the container is also able to connect with the host. And that means networking works between the container and the host. So now file system works, process isolation works, networking works, and the resource control also works. Now this actually feels like a real container. And just like that, we have built a working container runtime completely from scratch. No Docker, no Containerd, no Kubernetes, just Linux kernel primitives. And this is exact foundation modern container platforms are built on. So once you understand these Linux primitives, container stuff feels like a magic. So now you are no longer just running the container, you would understand how the container works under the hood. So if this series helped you to deep dive under the containers, hit like, share it with your friends, and subscribe for more content like this. Thanks for watching. I will see you in the next